Hi everybody, it's Mrs. Oleski here in my lovely, beautiful basement recording studio. For the most part, I'm not going to be having my face on these little flipped classroom activities. You get to hear my lovely voice. But I wanted to show you a little bit about a flipped classroom, and basically what that means is that I'm going to be teaching you things that we would have in class, like normal notes and things like that, as homework. And then when you come into class, we're going to be doing more complex enrichment activities so that we do the hard stuff in class, really, and that you do all the traditional note-taking and all of that kind of stuff as homework. So this series of PowerPoints that I'm going to be using, primarily, not always, but at least for the beginning, are going to be coming from your textbook. You can see it right here. This is Chapter 1, Chemical Foundations. Now, some of the things, I think most of the things you're already going to know. So I'm going to go through this kind of quickly. You can watch or you can take notes, but hopefully it'll be just a refresher. Okay, so the table of contents for Chapter 1 is listed here. And in the beginning, of course, chemistry is the study of matter. So this is a bit of an overview. The main challenge of chemistry is to understand the connection between the macroscopic world that we experience and the microscopic world of atoms and molecules. When you took physics, of course, that was the macroscopic world. Biology and chemistry tend to look at the microscopic world. You have to think on an atomic level. So, as you know, matter is composed of tiny particles called atoms, and atoms are really the smallest part of an element that still retains the properties of that particular element. Molecules are two or more atoms joined, acting together like water, H2O. Here we go. Oxygen atom, hydrogen atom, and then the water molecule. Oxygen and hydrogen molecules, although they're elements or atoms, sometimes we refer to these as diatomics. We use subscripts when more than one atom is in the molecule. So here's an oxygen molecule, O2, or a hydrogen molecule, H2. And remember the little phrase, I bring clay for our new house. Iodine, bromine, chlorine, fluorine, hydrogen, oxygen, and nitrogen are those elements then when written by themselves have a 2. And actually, even though they're considered, oxygen is an atom, O2 is considered a molecule. Chemical reactions. Now we're going to spend a lot of time in the future chapters on this. It's just an overview. One substance changes into another by reorganizing the way atoms are attached to each other. And of course we can balance equations and make sure that the number of atoms of one element are the same in the reactants and the products. So here we have this particular reaction we did at Parents' Weekend of Intro Chem, where I took water and it broke it up into oxygen and hydrogen. And you can see in the picture there are 2 hydrogen molecules being produced and 1 oxygen being produced. Oh, that's my cat. I didn't know where he was. Hello. He hears me down here. So, yes, he's very excited about this chemical reaction. The scientific method, obviously all science that you have done at Garrison or before deals with the scientific method, that orderly process. It's a framework for gaining and organizing knowledge. It's a plan of action, a procedure for processing and understanding certain types of information. We'll be doing lots of that, doing lots of labs. We're always challenging our current beliefs about science, asking questions and experimenting to gain new knowledge. So scientific method is needed. It's kind of an orderly process that we go through. Here are the fundamental steps of the scientific method. And you can see that after an experimentation, you may have to experiment again, change your theory, modify things. Law summarizes what happens, hypothesis is a possible explanation for an observation, and a model or theory is an attempt to explain why it happens. One of the things you'll have to remember is, of course, measurement. We do lots of measuring in chemistry. These are quantitative observations consisting of two parts, a number and some unit. So, for example, 20 grams. If you're weighing something out on a balance, and we have special balances in AP, 20 grams, or 6.63 times 10 to the negative 34 joule seconds. These are the SI units. I know you're all familiar with these. We don't really use electric current of amperes very much, although in electrochem towards the end of the year we will. But mostly we're focusing on mass, length, volume, and temperature. And of course, amount of a substance in moles. Remember, the abbreviation for mole is MOL. Here is the prefix system. And I know back in intro we had lots and lots of discussion about prefixes and their meaning and how to convert between different units. And essentially that's what you're going to be refreshing your memory on in Chapter 1. So here they are again. I'm sure this chart table 1.2 is also in your textbook. Why do we use prefixes? Because we change the size of the unit. We want to go from gigameters to centimeters, which, by the way, centi is not even on here, but nonetheless, we can use the prefix naming system. Here it is, the rest of it. Deci, centi, milli, micro, nano. These are other ones that are probably more familiar. Uncertainty in measurement. When we're taking a reading, sometimes we're not always right, and we have to make a guess. A final digit is the guess digit or the uncertain digit. It has some degree of uncertainty because we're humans and we're reading the instrument. We record the certain digits and the first uncertain digit or the estimated digit. So, for example, here is a volume of a burette. We will be using a burette when we do acid-base chemistry. There's a burette right there you can see close up. The liquid is read at the bottom of the meniscus right there. The meniscus of the liquid occurs at about 20.15. All right, you notice this one actually is read downwards. So the 20 is the long line, and then the 1. The first line is the 20, and then the 1. And then 0.1, so 20.1 is the first line, and then the 5 is an estimate. We estimated it's about halfway between the first line and the second line. Notice it's between 20 and 21. If you look at the entire burette, you can see that the first line is not a 21. So just keep that in mind. Sometimes we had some issues. I remember in intro chem when we had a quiz or we were reading the volume of things, sometimes people misread it because they didn't look at the markings. So the certain digits are 20.1, and the 5 is the guess. Somebody else might look at that and say it's 20.14 or 20.16, and those would obviously be correct as well. So there's always one uncertain digit in a reading. Accuracy and precision, you probably remember. Accuracy is the agreement of a particular value with a true value. How accurate are you? Are you near the true value? Precision is the reproducibility or the degree of agreement between different measurements of the same quantity. So if you are measuring something 3 times, you get the same number. You might be very precise, but you might actually not be very accurate. Perhaps there's something wrong with your scale. Here's a picture we've seen lots of. Accuracy and precision. Rules for counting significant figures. Now sometimes when we're working with numbers, we're talking about significant digits, significant figures. Now this particular book has the rules for significant figures. We taught the Atlantic Pacific rule, which I really like much better. So notice I will just be using the Atlantic Pacific rule in my discussion of significant figures, but we can see, you can read in green what the rules are, but I'm going to just look at the examples. So 3, 4, 5, 6 has 4 sig figs. There we go. And that's pretty obvious because Atlantic Pacific rule, the decimal point is absent. You'd be coming from the Atlantic Ocean. The little Pac-Man would keep eating until it hits the 6 and die away, and the 4 digits remain. Okay, another rule is, all right, there's the number. Again, I'm not looking at the green, I'm looking at the example. 0.048 has 2 significant figures. the decimal point is present, you come towards the left or the Pacific side. The Pac-Man eats all the zeros, and the 4 and the 8 are the two digits that remain, thus those are the significant digits, 2 sig figs. Here's another one. Again, just looking at the example, 16.07, decimal point is present, come from the left, 4 sig figs because the Pac-Man would die at the 1 and the 4 digits would remain. Here's two examples with another rule about zeros. The first, 9.300, has 4 sig figs because the decimal point is present. We come from the left. The Pac-Man hits the 9, dies, and 9300 are the 4 digits that remain. And then finally 150 has 2 because the decimal point is absent. Absent comes from the right or the Atlantic side. The Pac-Man eats the 0, and the 1 and the 5 are the only two significant figures left. And finally, it looks like in conversions, 1 inch equals 2.54 centimeters exactly. There's no rounding there. You don't have to round to 1 sig fig because 1 is with inch or anything like that. 9 pencils, that's how many there are. It has an infinite number of significant figures. So we never round to things that are equalities like that. So you can see those rules work well, but obviously I think the Atlantic Pacific rule works even better. You don't have to memorize the list of rules. Here's another example of significant figures. 300 point is written as 3.00 times 10 to the 2. It has 3 sig figs because we're looking at the fact in the scientific notation method the decimal point is present. We only look at the numbers before the times 10 to the second sign. That leaves 3 because you would be coming from the Pacific side or the left. What are the advantages of this? The number of significant figures can be indicated, and fewer zeros are needed to write a very large or very small number. Okay, here's the rounding rules. Again, I'm going to just look at the example and try to recall what we learned in intro. 1.342 times 5.5 equals 7.381. Wonderful. We round when we multiply to the fewer number of significant digits. And you can see 5.5 has fewer than 1.342, and so our answer has 2 significant figures, as 5.5 does. Okay, that's multiplication and division. Now, in addition and subtraction, it has nothing to do with significant figures. It has everything to do with decimal places. So here's an example. 23.445 plus 7.83 equals 31.275. Notice the example shows 7.83 has 2 places to the right of the decimal point. The 3 here is indicating it's the second one after the decimal. It's fewer than the 23.445, and thus the rounded answer has 2 places after the decimal as well. Significant figure and calculations. We'll be doing some of this in class. You have water in each graduated cylinder shown. There they are. You then add both samples to a beaker. Assume that all of the liquid is transferred. How would you write the number describing the total volume? This is a good question, and we're going to leave it for class. So we can talk about these things here, or I can show you these concepts, but then we can have a discussion in class, which is much better than hearing me drone on about the rules. So we get to some really interesting things in class. Oh, when they tell you it's 3.1. But I'm going to, we'll talk about ones like this again. What limits the precision of the total volume? So those are these thought questions that we're going to be start to do in AP Chemistry. Why are things the way they are? Dimensional analysis, huge. As you remember from intro, we did dimensional analysis all the time. We're going to convert from one unit to another. Here, I don't think I need to spend a whole lot of time. This is what this particular book's PowerPoint talks about, deriving the appropriate unit factor, and I'm sure you can do this. So I know I'm moving quickly, but of course you can always slow down and pause it and write down if you really want to write this stuff down. So here's an example. A golfer putted a golf ball 6.8 feet across a green. How many inches does this represent? Well, we know 1 foot is 12 inches. So we could write these 2 conversion factors. They're calling them unit factors here, 1 foot 12 inches and 12 inches 1 foot. So let's see how to do it. Derive the unit. Okay, so we're starting with 6.8 feet, and we want to get to inches. And you notice times we have to have something that is an equality. I usually put them in a parenthesis, but notice how these units cancel. And when you do, you just multiply across and do the math, and you get 82 inches. Notice that we round to two significant figures because 6.8 has two significant figures. We do not use the conversion factor in our rounding. Here's another example. What's the mass in the sample in grams? Okay, there's the 4.50 pounds. We use the conversion factor. Notice the units canceling. We don't have grams yet. We have kilograms. So we must keep going. Notice placing the units so they're going to cancel again. And this time we have to have three significant figures because of the number 4.50. We do not round using 2.2046 or the 1,000 grams. So 2.04 times 10 to the 3. Okay, 3 sig figs. Okay, another concept beginning chem, density, is mass per unit volume of a substance. There are always two units, grams per cubic centimeter, grams per milliliter are two common units for that. And of course, mass divided by volume. Most of this pretty straightforward. Here's an example. A certain mineral has a mass of 17.8 grams and a volume of 2.35 centimeters. What's the density? Pretty easy. You plug and go. Think carefully. How would you round? How many sig figs? Let's see what they do. So there you plug in. And how many? Hopefully you're saying 3. And yep, 7.57 grams per cubic centimeter. Make sure to put both the correct rounded answer and the unit. You forget one of those and you will lose points on the AP exam. So you do have to have the correct sig figs. Okay, here's another one. What is the mass of a 49.6 milliliter sample of a liquid which has a density of 0.85 grams per milliliter? Again, plug and go. Solve for the missing piece. The unit has to be unit of mass. Hopefully you know that's grams. 42 grams. Why 2 sig figs? Think carefully. Which number is the smaller? 0.85, right? Has 2 sig figs, so the answer is 42. And then finally, I think in chapter 1 they talk about matter. Anything that occupies space and has mass. Solid, liquid, gas. We don't need to go into great detail. Here's a nice little picture. You notice solid has a regular repeating pattern. The liquid, there's my kitty again. The liquid, actually in the case of water, the molecules are closer together. That's why it is more dense. You notice ice floats on water. And then finally gases. They try to draw it so you can see the little molecules moving around. And that's steam. What are some characteristics of these things? Solid, obviously rigid, has a fixed volume and shape. Liquid has no definite volume, has a definite volume but no definite shape. And it assumes the shape of the container. You know, you pour some water in a glass, it's going to take the shape of that particular container. And a gas has no fixed volume or shape. It takes on the shape and the volume of its container, and that's why they're compressible. And of course that gives a whole host of properties about gases that we will discuss later in the year. Mixtures, they have variable composition. They can be homogeneous, having indistinguishable parts like a solution, or they can have very distinguished parts like heterogeneous mixtures, things like sand and seashells. That would be a heterogeneous mixture. Which of the following is a homogeneous mixture? Here's a choice. Pure water, gasoline, jar of jelly beans, soil, or copper metal. The answer? Gasoline. Now some people might be thinking, well, pure water and copper metal are homogeneous. That's true, but they're not homogeneous mixtures. They're not made up of different component parts. Gasoline has different additives to it, but it's the same throughout in the end. And then physical and chemical change, being able to convert one thing to another. Some things change physically. Phase changes are physical, change in the form of a substance and not its chemical composition, like boiling or freezing. We can separate mixtures pretty easily. Distillation, filtration, and chromatography are things I know we talked about in intro, and you need to remember those particular meanings and the fact that you can separate things physically that way. Chemical change, however, is a little bit more interesting. Given substance becomes a new substance or substances with different properties and different composition. Often heating things up, except for in case of phase change, these things are often causing a chemical change, burning. In this case, a Bunsen burner. Methane reacts with oxygen to form carbon dioxide and water. That's a chemical change. It can't easily go back to what it was before. Here's a nice little diagram, organizational map of matter. A little bit different than we studied in intro, but this is perfectly fine. Matter, if there's variable composition, it's either a mixture or pure substance, and you can see where elements and atoms and compounds come in there. And then heterogeneous and homogeneous. This is a pretty helpful little picture. And let's look here. How many of the following are examples of a chemical change? So let's see the choices. Pulverizing or crushing rock salt, burning of wood, dissolving of sugar in water, melting a popsicle on a warm summer day. And hopefully you know it's just the burning of wood. Everything else hasn't changed the material chemically, and in some cases you can get the component parts back. Obviously, if you dissolve sugar in water, you can get water and sugar out again if you boil off the water. Melting a popsicle, I suppose you can freeze that again. So that ends the slideshow for Chapter 1. And so that's all we really need to know from Chapter 1 right now. Hopefully it's a quick little overview, and you'll be all ready to do the activities in class.